So we want to begin building some intuition about what happens in different types of collisions. There's two main types of collisions. There's plastic or inelastic collisions, and there's elastic collisions. If you have trouble remembering which one is which, just think about the names. Elastic is basically like rubber. So in an elastic collision, in a perfectly elastic collision, the objects will not stick together, they'll bounce off of one another. Whereas in a plastic collision or inelastic collision, after the collision, the objects stick to one another. When we're dealing with an isolated system, in terms of the mathematics, for an elastic collision, the kinetic energy is conserved, whereas for an inelastic collision or plastic collision, it's not conserved. A perfectly elastic collision, again, all of the kinetic energy is conserved, whereas for a perfectly inelastic collision, the maximum amount of kinetic energy is lost to some other form of energy. For both collisions, momentum of the entire system is conserved before and after the collision. But in this video, we want to, instead of focusing on the mathematics, we want to build a sort of intuition on what should happen in a simple collision. So we're going to look at 6 cases. For both the plastic and elastic collisions, we're going to look at the case when M1, which is the mass of object 1, is much, much smaller than object 2, which has a mass of M2. We're going to look at the reverse situation where M1 is much, much bigger than M2. And then we're going to look at the case where they're approximately equal. We're going to look at the simplest case where M1 is moving initially and M2 is stationary initially. So first, let me represent my objects with one of my beautiful diagrams. Let's just go over what everything is. These red circles here are our objects M1. These are going to be initially moving. And then the blue circles or purple circles are M2, which initially is stationary. And as you can see, in this case where M1 is much, much smaller than M2, we have this as being much, much smaller in size than this circle. And vice versa for this case where M1 is much, much larger than M2. And then in the middle, we have them being approximately the same. So as I said, in this video, we're not going to focus on the actual mathematics as much as just try to build an intuition for what should happen during and after the collision. A good way of doing this is to think of a real-world analogy for each type of collision. There's many different examples you can choose from, and these analogies will help you visualize what the motion of each object should look like before and after the collisions. So let's start off with this case M1 much, much smaller than M2. In this case, we can think of this object M2 as more or less like a wall, because it's first of all stationary and it's much, much more massive than this object. And this object, for the plastic case, let's imagine it's a small piece of Play-Doh or silly putty. So you can imagine throwing a little piece of silly putty at a wall. Maybe it's the wall on an ice skating rink or something. So technically the wall can move, but because this mass is so much smaller than this mass, in most cases, what's going to happen is after they collide, this is just going to stick to this object and they're going to remain basically stationary. For the elastic case, again, we're treating M2 as almost a wall, some massive object. And in this case, M1, let's imagine that it's a tennis ball or some very light bouncy ball. So if we throw this object at the wall at M2, then what's going to happen is it's just going to bounce back at us at nearly the same velocity at which it hit the wall. And again, M2 in this case will barely move. It will seem to appear stationary. Let's now jump over to the third case where M1 is much, much larger than M2. So in this case, you can imagine that M1 is a bus or a truck that's driving along the highway at some velocity, and M2 is some fly or insect that's just floating around minding its own business when all of a sudden the bus collides with the truck. So what's going to happen from the perspective of the driver of this bus? Well, he's not going to really notice the bug that he hits. Obviously, the bug is going to stick to the windshield of the bus, and this bus is just going to basically move at the same speed with which it was moving before. For the elastic case, where M1 is much, much larger than M2, you can imagine that you have some football or soccer player, depending on which country you're from, and he kicks a light ball, a soccer ball, which is initially at rest. So the player has a lot of muscle in his leg comes flying down, it makes contact with the ball, and it's not going to come to a complete stop. It's going to still move in the same direction, more or less, at more or less the same speed as it was before, but the ball is going to fly forward faster than the leg of the player. And you can easily try this at home if you just kick a ball. Well, maybe not at home, maybe outside of your home. Just kick a ball and you can easily see that the ball, depending on how light it is, should move faster than the speed with which you kicked it. Last, we're going to look at the case where M1 is approximately equal to M2. And again, in the plastic case or the inelastic case, the objects stick together after the collision. So initially, what's the momentum of the system? We only have m1 moving with some velocity. And after the collision, both these objects stick together. And because the masses are approximately identical, we can treat the mass of the object after the collision as being twice the mass, the original mass m1. And because momentum is conserved, we know that the velocity after the collision should be 1/2 of the velocity from before the collision, 1/2 of the velocity of m1. And again, these two objects will move together. In the elastic case, however, what's going to happen is that after m1 makes contact with m2, m1 will come to a stop, it will come to rest, whereas m2 will continue traveling at approximately the same speed with which m1 hit it. And you can see this for yourself if you have a pool table or a billiards table. Just take two balls, take the white ball and any other ball, and you'll see that when you strike the white ball against the other ball, then the white ball basically comes to a stop and the other ball moves. It may be hard to tell, but it moves with more or less the same velocity with which the white ball hit it. Now the exciting part, let's run an animation of all of these collisions and see that indeed this what I described is what happens. Okay, and indeed that's basically what happens in all the cases. First, let's start off with this case, the plastic case. As we said, this is like throwing a small piece of silly putty at a wall, and as we expect, the silly putty basically just sticks to the wall doesn't move, it barely notices it. For the elastic case, the tennis ball or whatever ping pong ball, it bounces back at more or less the same velocity with which it hit the wall, and again, the wall barely moves. Now, for this third case where m1 is much, much bigger than m2, again, our bus, our massive object, continues moving at basically the same speed with which it was moving before, and m2, the small object, the fly or the insect, is just carried along. It's just dragged along on the way. Whereas for the elastic case, again, m1 basically is moving at the same speed. It's slowing down a little bit, but you can see that m2 is moving much faster than m1 originally was. And last, we have this case where the two masses are basically equal. As you can see, they stick together in the plastic case, and maybe it's hard to tell, but you can definitely see that after the collision, it's moving slower than before the collision. Whereas in the elastic case, m1 comes to a standstill, whereas m2 is moving at more or less the same speed at which m1 originally moved at. So let me pause these. As I said, in this video, I'm not going to focus so much on the mathematics, but let's just quickly go over the mathematics for the inelastic case, for the plastic case, because this is going to be the simpler case to deal with than the elastic case. So again, for an isolated system such as these ones, we know that momentum is conserved before and after the collision. So first we write the conservation of momentum equation for, let's look at this case, m1 much, much smaller than m2. So over here, I have my momentum equation. Remember, initially m1 is the only object moving and m2 is at rest. So the initial momentum of the system, which is only these two objects, is initially m1 v1. And then remember, in the plastic case, they stick together, meaning that the new object, here, let me run the animation again a little bit. You can see they're stuck together, and now this object has a mass m1 plus m2, and it's got some new velocity, even though it doesn't look like it at the moment. But we'll call this new velocity u. So the velocity after the collision, to find that, we just have to divide by this parentheses term, and we get u is equal to m1 over m1 plus m2 times the original velocity v1. And this actually explains the other two cases as well, because let's think about it for a moment. First, we have the case where m1 is much, much smaller than m2. So you can imagine that m1 is nearly 0, or just if it's much, much smaller than m2, then if you look at this fraction over here, then the m1 is negligible compared to the m2, and this fraction is approximately equal to 0. So 0 times anything is 0. So that's why the velocity in this case, the velocity u, is approximately 0. On the other hand, when m1 is much, much larger than m2, the m1 dominates in the fraction, and this fraction is approximately equal to m1 over m1, which is just 1. And that's why the velocity after the collision is approximately the same as the velocity before the collision, because we can basically ignore the m2 in this case here. And finally, in the case where the two masses are approximately equal or are equal, then obviously this fraction is approximately equal to 1/2, and that's why the velocity after the collision is equal to 1/2 of the original velocity of m1. We will look at the equations for the elastic cases in a later video. Again, they're a little bit more complicated. And also in this video, we only looked at the simplest cases of two objects colliding, one moving, one initially at rest. But again, this is just to help build some intuition for the various results that you should see for each type of collision. Hopefully it was pretty straightforward. And with that, we can move on to the next video.